Section 4e and the next section 4f are both about exponential functions. So what do they look like? Well, they look like that right there, where it would be a function of the form f of x equals a raised to the power of x, where a is a number, but there are some restrictions there. You can't have a be 1 because then you would always just get 1 no matter what. Then that's just going to be a constant function. And you need to have a being positive. If you try to do this with a negative a, you get a huge mess, basically. So what do they look like? The first thing that's noticeable, I think, is that x is in the exponent. So we have x in the exponent, which is not where it's been previously, right? Usually that's the base. And the other thing is that whatever that a is, whatever number is, it needs to be positive. So I'm just going to say that we have to have a positive base, since that's what that would be called, right? You have your base and your exponent, where here a is your base and x is your exponent in that general form. You can apply transformations to exponential functions. So just like when these came up before, it's the same ones, realistically. So you can have the stretches and compressions and the shifts and the reflections and all that. Although the reflections you don't really see as often, but you can have them. So I didn't put that in here. Plus one of them you can manipulate a little bit into just turning it into a different base. And then it just ends up being like a regular old exponential function. So you can still have the vertical stretches or compressions though. So that first one, the 3 times 5 to the power of x, I've got a vertical stretch of 3. Then the horizontal stretch or compression, where there's a 2x in the exponent instead of an x, that's actually going to be a horizontal compression. But then these other ones, the vertical shift, that's where we just have a number added or subtracted at the end, just like before, right? Just like with a parabola, if you had like x squared plus 2, then that plus 2 at the end was the vertical shift up 2. It's the same idea here. That plus 1, that's just a vertical shift up 1 of what the graph of 7 to the power of x looks like. Horizontal shift, just like before with the parabolas, when you replace x with x minus something, that's a shift to the right. And if you replace x with an x plus something, that's a shift to the left. So where there's the x minus 3 in the exponent, that's actually a shift to the right of 3 units. And then you could do everything all at once. It looks like that's got a vertical compression, horizontal compression, a shift to the left, and a shift down. That would be a lot to do all at once. But we're not going to have any that have 4 things going on. Maybe 3 when we actually get to like making the graphs and stuff. Definitely 2. We'll have several where we've got 2, maybe once in a while 3. 4, that's a little wild. I don't know if we need to go there. Plus, if you have 4 of them, it's really hard to get it to where the points that you're plotting don't have like weird obscure coordinates. There's also that. So it ends up feeling really inaccessible because of that, realistically, right? When you're plotting a y coordinate of, 27/14, that's, and I guess you go, yeah, it's a little below 2, but still, it feels tougher with the weirder numbers. So anyway, first things first, the one big thing in this section is if you're given a bunch of functions and you have to identify which ones are exponential functions and then which ones aren't. So the things that we're looking for, it's not on the screen right now, but let me just scroll back up to get it. It's the thing that's in blue. You want to see the x in the exponent, not in the base, and the number that's in your base can't be negative. So looking at a, that's the problem. So a with negative 4 raised to the power of x, the base is negative 4. So with this one, this is not a function, or not an exponential function. So not an exponential function. And the reason why not is because there is a negative base, right? The base is negative 4. That's a negative number, and that's the thing we can't have. B, however, is okay. because even though b looks like a just without the parentheses there, you're raising 4 to the power of x and then negating whatever that is. That's okay, right? This is actually the equivalent of -1 times 4 to the x. And it's okay to have the -1 out here. That's a reflection, right? That's fine. So this is actually okay. So this is a yes. This is an exponential function. Because we've got the base of 4, that's positive, and then x is up in the exponent where it's supposed to be. C has a lot going on. So, I mean, I guess if you were going to build it up from just a basic exponential function and then doing the transformations to it, you would start with the 2 to the x, and then you've got that vertical stretch, that multiplication by 9 out front. Then you get the vertical shift, the +3 at the end. But when you look at it, you go, x is in the exponent. The thing that's the base, it's just the 2, right? I mean, it's the thing that's being raised to the power of x. So this one's fine, right? So that's a yes. Right, I guess I can put y in parentheses here, right? So we got x in exponent and positive base. Those are the two things that you need, right? So C, if I wrote that in parentheses, I'd be writing the exact same thing. So I'm going to skip over it here, right? Once we have one yes, I think maybe we kind of have that established now. But it's the same thing, right? X is in the exponent in C and the base is positive. D looks different, but let's see. X is in the exponent where it's supposed to go. And then the base, it's a fraction, but that's okay because it's a positive fraction, right? That was the only requirement. It had to be positive. That's fine if it's not an integer. 1/2, 1/4, 3/26, whatever. Positive fractions, those are fine. So this one is also a yes, even though it looks a little bit different because of that fraction. That's okay. As long as the fraction's positive, we're good to go. E, looks like we got a problem because the base is x, right? X is in the wrong spot here. So this one is a no, or I guess like I said, an A, not an exponential function. And the reason why not is that x is not in the exponent. And then you can say the same thing about f, right? Even if you try to manipulate f a little bit, which you could rewrite the 1/x as x to the -1. So even if you tried to manipulate this thing just to find out or just to make sure that this doesn't work, you could rewrite it as x to the -1 squared, but there's an exponent rule where if you have a power raised to another power, you can multiply them together. So you could write this as x to the -2. And it looks like we have the same problem, right? X is in the base, it's not in the exponent. All right, so then this one doesn't work either for the same reason that E didn't work. So this is not an exponential function. And it's for the same reason because x is not in the exponent. So E and F, those are still functions. They're just not exponential functions. I can tell you what they look like. E looks kind of like this. I guess it would be steeper on the left side. I didn't draw that too well, but it has kind of like an S shape sort of. And then F, I know what that one looks like too. It kind of does this. So they're graphable and they're functions. They're just not exponential functions. All right. Let's see. Then the next thing is evaluating functions. Let's see. So basically just subbing in and simplifying, but it feels a little bit different with the x and the exponent. And this is one of those things where if you're used to it, then it feels fairly natural. But if this is a thing that you're not that familiar with, the first couple of times this feels kind of awkward. So I figured it was worth going through kind of a page worth of these. So that's kind of the way that I have this set up. So we are just going to sub in and simplify, but it does feel weird when you're subbing into the exponent. So let's see. Number 2, we want f of 1. So f of 1 here, if I just sub in a 1, it'll be 5 raised to the power of 2 times 1, and then plus 2. Well, 2 times 1 up in the exponent, that's a 2. So this is 5 squared plus 2, but 5 squared is 25, so we got 25 plus 2, which is 27. All right, there we go. Number 3, we're going to do the same thing, so we want f of 2. So f of 2 would be 3 times 2 raised to the power of 2 minus 4. But 2 minus 4 is negative 2. So this is 3 times 2 to the negative 2. And that part, I would say the best thing to do is to rewrite that with a positive exponent. And the way that you can do it is bring it down. So you could write this as 3 times 1 over 2 squared. So now that I've got this down in the denominator, I can write it with a positive exponent. So notice how I've got the exponent of 2 instead of negative 2 now. But then the 2 squared is a 4. So this is 3 times 1/4, which most people just call 3/4. All right. Next one, number 4, we want f of 0. All right, well, f of 0, it'll be 1/4 raised to the power of 0 plus 2. But 0 plus 2 is just 2. So we can say, well, that's 1/4 quantity squared. And there's an exponent rule for this too. When you're raising a fraction to a power, you can basically distribute the power to the numerator and denominator. And I think that's what we want to do here. So we'll say this is 1 squared over 4 squared, and then 1 squared is 1, 4 squared is 16, so 1/16 is what you get there. And then the last one where it looks like we got an awful lot going on, but the fact that we're going to evaluate the function at -1 is really going to shorten this up. Because we're going to have f of -1, which will be 8 times 5 raised to the power of -1 plus 1. Then we've got a plus 3. But -1 plus 1 is 0. So this is 8 times 5 to the 0 plus 3. But when you raise anything to the 0 power, I guess anything other than 0, but since the base has to be positive, we're not going to run into that problem. So for our purposes, you raise anything to the 0 power, you get 1. So that 5 to the 0, that's a 1. All right. And this is 8 times 1 plus 3, or 8 plus 3, which is 11. All right. So the thing that happens in number 5, where when we subbed in the -1, that gave us a 0 in the exponent, using, and when we get to the graphs, using the x value that gives you a 0 in the exponent, that's a really good move. Basically, that'll kind of center the thing that you're graphing. So you'll be picking the point that's in the middle, and then you just go kind of in both directions to get the rest of it. So when we get to the graphs, that's actually a really important move. As far as, I guess, compressing how much time you would have to spend on a graph, which is a nice thing, right? There are other ways you can get the graphs, but this would make it faster. There is one other thing I want to point out here. So I got a little bit of extra room, and I left it for this reason. So if we just start evaluating this function, I can pick any of them, but this is the one that's sitting here, so we'll just use this one. What if I just wanted f of 0 instead? Well, then I have 8 times 5 raised to the power of 0 plus 1, and then plus 3. So this is 8 times 5 to the first plus 3. So it's 8 times 5, which is 40, plus 3, and you get 43. That's a big jump, right? Because x goes up by 1, y goes up by 32. Oh, if that looks like a big jump, let me see what happens next. So now if we want f of 1, then we're going to have 8 times 5 raised to the power 1 plus 1, and then plus 3. So this is 8 times 5 squared plus 3. But 5 squared is 25, right? So this is 8 times 25 plus 3. 8 times 25 is 200. So that's 203. Okay, that's a bigger jump, right? We went up 32. Now we're going up by 160. Why don't we do one more? F of 2. 8 times 5 raised to the power of 2 plus 1, and then plus 3. So that's going to be 8 times 5 cubed plus 3. 5 cubed is 125. So we're going to have 8 times 125 plus 3. But 125 times 8 is 1,000. This is 1,003. So we go up by 32. Then we go up by 160. And then we go up by 800. Whoa. Right? So look, and the x values, we're just kind of innocently going up one at a time, and the function's doing these crazy things. This is what exponential functions do. When they increase very, very rapidly. And you'll see it in the graph, because basically what the graphs look like is that there's one part of the graph that's really sharp. Like one half of it will be really, really steep. And that's kind of what we're working through here. And that's why there are these huge, huge jumps. But that actually helps as far as like trying to model things in real life, that this is how these functions behave, believe it or not. There are a lot of things that end up behaving like this, either natural things or man-made things. So exponential functions do increase or decrease very rapidly, right? We just saw that, right? The jumps were getting bigger and bigger and bigger, and almost right away they're getting ridiculously huge, right? Like that last one was a jump of 800. That's enormous. But as a consequence, they end up being really useful to model things that, like I said, things that occur in nature and things that are man-made. So either kind of change, either things that get big really fast or things that kind of deprecate or shrink down really fast. So when do these end up being helpful? When you have a quantity that increases or decreases at a rate proportional to its size. So basically it's if the quantity gets bigger, then the rate of change increases. So the rate at which it gets bigger also gets bigger, to put it another way. That's pretty much what happens. And that's why those numbers are going crazy on the last page. If I scroll back to that, so as the x values are getting bigger, the jumps here get, like, not only do the values themselves get bigger, but so do the jumps, right? Jump of 32, jump of 160, jump of 800, right? So that's when this actually ends up being a thing that turns out to be useful. But it actually shows up a lot. So like it says in that third bullet point, continuously compounded interest, because when you're compounding interest, you apply the interest to, like, if it's, if you've been through like several periods, like you've been through a few years or something, you don't always use the original amount. You use what was in there at the beginning of that year, right? Which would increase over time, right? It gets bigger and bigger and bigger. So then continuously compounded interest is, instead of doing it every year, or every month, or every day, it's just you're doing it all the time. And so that basically gives you a situation where the amount that's in the account is always getting bigger, and that's forcing the rate of change to keep getting bigger. And so this ends up being a situation where we can apply this sort of function. Size of the population. So like a population of humans, population of a bacteria, that's the one that follows it really well. Population of humans, there are going to be other factors too, right? Like if there's an area where like a big employer suddenly relocates, right? Like that's going to have a huge effect. But like the size of a bacteria population definitely behaves like that. Decaying radioactive material, so that one would be a decrease, right? And temperature difference between a hot object and the air surrounding it, that's also going to be a decrease, right? Because then, right, like you take a cup of coffee and you put it on the table and leave it there, the coffee gets colder, right? It doesn't get warmer. So that's a decrease, right? That temperature difference, right? Eventually it'll get down to 0, where then the coffee would be room temperature. All right, so the formula that we're going to use is going to be this. So exponential change, either growth or decay, it looks like that, where P is the principal amount or initial amount. You see P used more often than like an I symbolically. So we'll use a P. And plus the PERT, the P-E-R-T, that's easier to remember, I think, anyway. Maybe that's why that's the one that's used. R for rate. So that can be the rate of growth or the rate of decay. For growth, you'd have a positive R. For decay, you'd have a negative R. If you have a negative R, then the e to the RT part of it will be less than 1. So then when you multiply by P, you'll end up with less than what you started out with. So that's what a negative exponent will get you. But generally that's how it works, and that is a big thing, which is why it's in bold, that if you have exponential growth, you should have a positive rate, exponential decay, a negative rate. T is time, so elapsed time. So like after 7 years, how much money is in the account? That kind of thing. And then T would be 7. And then A of T, that's just the amount after time T is elapsed. E is a constant. That's one of those things where it depends on if you've done a lot of stuff like with logs. Because like if you've had a math class before where you talked about natural logs, you've definitely talked about E. Because the function e to the x and the function natural log of x are inverses of each other. And natural log you could write as log with a base e. So if you've talked about one, you must have talked about the other, right? But not everyone has had a class with logs in it. That's usually a thing that I think most people encounter in pre-calc, but that's one of those things where different states have different requirements, and some people are going to see that in high school and some people aren't, right? It's one of those things. Or some people might have had a pre-calculus class before and been like, oh yeah, I remember that thing, right? But not everybody. So if you haven't seen it before, E is a constant. So kind of like pi, where pi is an irrational number, where it's 3.14 or whatever. E is kind of the same way, where it's an irrational number, about 2.718. That's the 28. I actually didn't remember. I had to use a calculator to get that part. I just remember 2.718. That's roughly that. But the most common way of defining what it is, as n increases, 1 plus 1 over n to the nth power will approach that. If you, and just for a concrete example for that, if n is I think if you use 1,000,000, you'll get it correct to 5 decimal places. So if n is 1,000,000, then 1 plus 1 over n to the nth power ends up being about 2.71828. So, I mean, with a gigantic n, you would get there. And that's one of those things where to do like the full-fledged definition of what E is, you need a thing called limits, which is like the first big thing that you would cover in Calc 1. But I think we can kind of talk about the idea without going into all the limit stuff and just say like, as n gets bigger, you would get closer and closer to what E is with that 1 plus 1 over n to the nth power expression. That's what it is. I mean, I would rather go through a little bit of that than just to be like, oh, it's this number that just sort of appears. It ends up being really useful, but that's where it comes from. And that formula up toward the top, the A that I have circled right now, A of t equals p e to the rt. Sometimes that's expressed differently, like with different symbolism. You see it like that a lot too, where that a sub 0 is supposed to be the amount at time 0. And you see that in place of the p for principal. Then sometimes you see k instead of r. It just kind of depends on what class you're seeing it in, I guess. It's one of those things where if you see it in a math book and if you see it in like a physics book, they might use slightly different notation, but it's the exact same thing. And that's kind of what I'm trying to say in that last bullet point. Just if you look at anything else, like if you try to look this up online, you might see different symbols. That's fine, right? Ultimately, the symbols are really just kind of functioning as placeholders, where it's like, okay, this thing that's out front in front of the E, that's the original amount, right? Whatever symbol you're going to use for that, if it's a sub 0, if it's p, whatever. So there are other common ways of expressing it, but I'm just going to stick with the p e to the rt. I think that's the easiest one to get to like stick mentally. That's the one that always stuck for me, so it felt like the right one to go with. All right, so number 6, we've got our function for the growth of a colony of bacteria. A of t equals 100 e raised to the 0.045 t. So A, the amount is measured in grams, and then T is time measured in days. All right, so first, the initial amount, where that is in the function, well, that's the thing that's out front. It's in front of the E. Basically, it looks like a constant. It looks like a constant multiplier. So here, P, the initial amount, looks like it's 100 grams. And then B, the growth rate, that's the number that's multiplied by t in the exponent, right? Like p e to the rt. The r, in this case, being 0.045. So we can say that r is that. Or if you want it in percent form, because when these are written out in words, usually that's the way they show up. So that would be 4.5%. And then C, what's the population after 5 days? So for C, we're really just going to evaluate that function. It's saying if t is equal to 5, what's A? Or what's A of 5? And then we can just sub in and say, well, that's 100 times e raised to the power of 0.045 times 5. But 0.045 times 5 is 0.225. So this is 100 e to the power of 0.225. And this would be a point where you would probably want a calculator. Trying to do that by hand is a little bit rough. It depends on what sort of calculator you have. If you have a TI, like anything in the 80s range, like one of them, like anything with this long rectangular shape, one of the graphing calculators, the E is a secondary function. I can show you where it is. It's like where there's that natural log key that I'm pointing at right there. There's an e to the x on the body of the calculator. So you need to use the second key in the upper left and then that key, and then that would do it. But it depends on what kind of calculator you have. If you have a calculator that's specifically for business, there may be an e raised to the power button. Let's see, I have a Casio here too. Does that have one? No, that's also a secondary function here of natural log. But there are ones that have like an e to the power button, and it's going to vary. Let's see, I'm trying to think, because the three that I have to kind of prepare for are Texas Instruments, Casio, and Calculated Industries. If you have a Calculated Industries one, those are so different, like the models are so different because they're so geared towards specific occupations. I think if you have the business one, because there's like a real estate / business one, that one I believe has an e to the power key, because there you would use continuously compounded interest a lot. The other ones, like, because I know there's like a pipe fitter one, the surveyor one, there are a few different ones. I'm not sure about those. I guess it would depend on which model you've got. If you're not sure, then I guess email me and I could look it up and figure it out. But But yeah, it's gonna vary depending on what kind of calculator you've got. But in any event, what this ends up being, at least at two places, is about 125.23 grams. So that's what we end up with there. So just substituting in the way that you would do the 100e to the 0.225 in your calculator. I mean, I guess it depends on what kind you've got. If you've got like a graphing calculator where you can put multiple algebraic steps in a single line, you could just have 100 times. And then if you use the e to the power function and just put 0.225, that would do it. If you don't have a calculator that can handle multiple algebraic steps at once, you could just do e to the power, like e to the 0.225, and then enter, and then whatever that is, then just multiply by 100, right? I mean, you're multiplying, you can do that in the opposite order. That's fine, right? You'll get the same thing. And you might have to do that depending on what sort of calculator you've got. All right, next, there's some continuously compounded interest. So 2,500 invested in an account earning 5% interest per year compounded continuously. So how much money would be in the account after 8 years? Okay, let's see what we're being given here. So the 2,500, that's the initial amount invested. So that's P, right? That's our initial amount. 5% interest per year compounded continuously. It looks like there's our R. And then after 8 years, that's the elapsed time. So it looks like that right there is our T. So what we've got is that P is 2,500. We've got that R is equal to, and I'm going to convert this into decimal form because when we sub into the formula, that's the way we're going to need it. So move it 2 places to the left, right? So 0.005 written as a decimal instead of a percent. And then T equals 8. All right, so generally what we have is that A of T equals P e to the RT, right? So if I sub in here, now what we've got is that A of T equals 2,500 times e raised to the power of 0.05 times 8. But 0.05 times 8 is 0.4. Right? Oh, I'm getting ahead of myself. Or I guess I need to rewrite that T. I'm not getting ahead of myself. It just looks that way because that I could have pushed that and said that was an 8. Right? Since that's what T is going to be when we sub in. So that should have been 8, not T. Sorry about that. I was confusing myself with that. But yeah, that exponent's a 0.4. So you'd have that A of 8 is going to be 2,500 times e to the 0.4 or 0.40. And then using your calculator, what you end up with is that A of 8 is going to be equal to 3729.56 right? So I guess $3,729.56. That is rounded off. I think generally the homework asks you to round to 2 places, so I'm going to stick with that. And this is money anyway, right? Like that's probably how you would round that off anyhow to the nearest cent, right? Like to the nearest 10 cents sounds weird. So the nearest cent, 2 places. That seems like it's pretty sensible. All right. Then we've had some growth, right? Because this one got bigger, right? Because the initial amount was 2,500 after 8 years. That's a bigger number. Number 6 was also one that got bigger, right? Started out as 100, got up to a little over 125. But 8 is not going to get bigger. And the big key red flag word for that is this one right here, that it decays. So I don't know if that should properly be pronounced as seaborgium or seaborgium. But whichever one it is, it's a synthetic element. So like it's a man-made element that's used for fusion. So hot fusion, cold fusion. And with the man-made elements, right, I guess this is one of those old chemistry things, right, where if you have a man-made element that's some like a kind of unusual isotope, they tend to break down really fast. right? They decay really quickly. Like the radioactivity goes away pretty fast. So that's what we've got here. So that isotope, the seaborgium or seaborgium 266, it decays at a rate of 2.3% per second, right? Like that seems rather quick. So how many grams of a 180 gram sample would remain after 90 seconds? So let's see what we're being given first. So the decay rate, it's 2.3%. I'm going to write that as a negative because it's decay. So R is negative 0.023. And the negative is because of the decay. That's the big thing with this problem, right? It's a decay. It's got to get smaller. So you got to have that negative exponent. So you need the negative R. Then the initial amount, P is 180, right? 180 grams. And then after 90 seconds, that's our elapsed time. So we'll say T is 90. All right. And so we're going to use, again, A of T equals P e to the RT. So now A of 90 would be 180 times e to the negative 0.023 times 90. That exponent simplifies to negative 2.07. So A of 90 is 180 e to the negative 2.07. And if you put that into a calculator, you should get about 22.71 grams. So either, whichever kind of display your calculator has, in order to get that to be a negative number in the exponent, you've probably got a key that'll change the sign. So you probably don't want the minus. There's probably like a negative sign inside of parentheses. If you've got a TI, you've got that. It's probably down by the enter key, somewhere toward the lower right. Depending on which model you've got, it's not always in the exact same spot. I think with the ones that are like the TI 80, whatever, like 83, 84, 86, they're all kind of like right next to it, like to its left. But there are also ones where it's right above it. So it's somewhere down there. But in any event, that's what you should get, 22.71 grams, at least rounded to two places. And if you look at that and think, that's really small, considering that it's only been 90 seconds, right, to go from 180 to 22.71. Yeah, but that decay rate is per second, right? So that 2.3% per second, with that going on, 90 seconds is actually kind of a long time, at least in a relative sense. So yeah, you end up with something kind of tiny, relatively fast. Then number 9, this is another decay, because this is depreciation. So it says that a Chevy Malibu decreases at a rate of 12%, or depreciates at a rate of 12% per year. So it depreciates. That's the key word here, because that means that the price is going to decay, right? That's not a growth, right? Depreciates if the price is going down, right? Not going up. So, all right, well, we've got that. Then that would mean that when we wrote out what the rate is, it should be a negative again. So negative 0.12, converting the 12% into decimal form. And then if a particular Chevy Malibu is worth $22,000 right now, so we're going to treat that like it's the initial amount, like we're starting, like the time clock starts now to go forward to 2027. So we're going to treat that 22,000 as the initial amount. So that's our P. And then the elapsed time, it doesn't come right out and say it, but you can figure it out, right? It's going to be 7 years, right? From 2020 to 2027. So it looks like T is 7. And then we're going to use the formula that we've been using. So A of T equals P e to the RT. And then that means A of 7 will be 22,000 times e raised to the power of negative 0.12 times 7. So that exponent is a negative 0.84. So 22,000 e to the negative 0.84. And then what that should simplify to is, let's see, I've got it over here somewhere, 94, 97, 63. All right. And I guess for completeness' sake, just with the context here, it's true that cars and vehicles in general don't really depreciate at a continuous rate, right? They depreciate a lot more, like right when you first get them, right? Like the whole thing about, you lose 20% of the value when you drive it off the lot or whatever. Um, I don't know if it's quite that, but it's big. And the depreciation is much steeper at the beginning, and then it kind of levels out over time. So maybe this model is a little bit simpler than what would happen in real life, but it's workable, right? And we can still figure out what to do with this sort of problem. And this sort of thing, like where it's the depreciation of a car, this does show up in the homework assignment. So I figured it was worth throwing one of them in there. Even though if you're looking at it and thinking, that doesn't work continuously. It depreciates a lot at the beginning, and then if your car is really old, it would barely depreciate at all. Yeah, that's true. But I think we'll be okay with not having like a perfect model here. All right, so I think that would basically do it for 4E. So you have those problems where you have to pick out, which ones of these are exponential functions. There are some evaluation problems, and then there are a few of these growth and decay ones. The biggest thing with the word problems really is just figuring out if it's growth or decay. Because other than that, I think you'll be able to pick out the initial amount and the rate and the amount of time pretty quickly, right? Because you'll have the numbers in there and be like, oh, that's this one, that's this one, that's this one. But whether it's growth or decay, that's going to determine if you have to make the rate negative, right? Since you would for decay. So that's probably the biggest thing. If you can do that, I think you can do it. So yeah, I think that covers everything for 4E.